All right, everyone, we're going to start our next session here with a presentation from our friends at the University of Washington, Ricky and Suresh, finding crosswalk types, tactile pavings, and sidewalk widths at scale with AI.
Thank you, Zhang.
Yeah.
Okay. Hi, folks. My name is Suresh Devalapalli, and this is Ricky. We are from Gaussian Solutions. We work in collaboration with Tasker Center. Oh, yeah, Amy right there at the University of Washington. Today, we are here to present our work that we did with the state of Washington to map their pedestrian infrastructure. There's a talk tomorrow that will go into more details, but today it's about finding the crosswalk types and tactile pavings and sidewalk widths. So just as I mentioned, like state of Washington is huge. It's about 184,000 square kilometers, very huge. Doing mapping in such a huge area is pretty much impossible manually. Anyway, we finished that whole thing using AI. When we finished, the sidewalks count is about 36,000 kilometers of sidewalks in state of Washington, about 6,700 kilometers of crossings, and 133,000 intersections that were mapped. So as I mentioned, tomorrow we'll talk more about the base AI, but today we are talking about the extensions that we built. The base map gives us the line string information about where sidewalk, crosswalks, etc. exist. And the extensions that we built so that it can be used with any other line string information is about finding what type of is there a tactile paving at the curb nodes, what type of crossings we have, and the sidewalk width. And to talk about the AI that we used to do this, Ricky will talk about it.
Thank you, Suresh. Okay. So we have three extensions that we developed on top of our core systems, the automated mapping system. So the first one is the extension number 1, which is the crossing type classification here. So the goal here is that for each line string that's tagged with crossing on OSM, either it's generated from our automated pipeline or it's already be entered onto OSM by other mappers. We want to tag this as marked or unmarked, and then for marked crossings, we would like to further divide it into what type is it. Is it zebra crossing or is it other types? And we want to use AI to sort of automate this process to reduce some human efforts and the time needed to just go over every single crossing strings. So yeah, when we build our model, the first step is to create a data set. For this classification task, we collect around 8,000 images at the zoom level 19, center around each crossing line strings on the OSM data set we have. And then we label each of them as a yes for marked and then no for unmarked. And for the marked crossing, we further divided them into zebra and other. And now that we have a data set, we can work on the modeling part for this task. The first step is to load the images and then do some standard pre-processing, including data standardization, data augmentation, and then after that we can fit it into our model. Because this is a 3-class classification task, which is relatively simple. So we use a very lightweight model, the mobile net with 3, just to avoid some overfitting for the degraded performance. So once we train the model on our label data, and when we input a new images of the crossing, the model can classify it as unmarked or zebra and others. So how does our model work? How well does it work? I mean, we have the evaluation number here on a held out unseen data set that was isolated from the training. So it represents a fair performance of model in the real life scenario. So we have a precision number of 0.8, recall number of 0.89, and then the overall F1 score of 0.84. You can think of this number as like 84% of the classification that come out of our model is correct. That can be directly go back to OSM. And for the rest 16%, there are some challenges that we are working towards addressing it. The most common one being the shadow coverage or the tree coverage. So the idea here is that if it's not visible in the image, if the model can see what's underneath the tree, it cannot put out a correct prediction about what type of crossing it is or if there's a crossing. So to address this challenge, we are working on incorporating additional orthogonal data sources, which is the street view imageries. So we are working on using multiple sources of data to help this classification task. The other challenges are the out of distribution crossings. It could be special types, which rarely occurs in the training data set, or it could be other cases where the other infrastructures just look very similar to the crossing lines from the aerial view. Yeah, we are expanding our data set to incorporate more of these out of distribution samples to make our model more generalizable. And that was the first extension we have. Extension number 2 we have here is the tactile paving detection. And the goal here is that for each, around each curb nodes, we want to detect if there is a tactile paving or no. Again, the first step is to prepare a data set. For this detection task, we gather 4,000 imagery patches that sample around the nodes that's being tagged as very close to the curb or curb close to lower. That's where the tactile paving usually occurs. And then we assign a binary label for each of the patches, positive being there is a tactile paving in this patch, and negative being there's no. And we move on to modeling. The first step is still the data pre-processing, and then we added a second step to use a pre-trained framework, a ResNet, to do feature extraction, just to extract the key features of these input images for later processing. And then for the actual classifier, this tactile pavement detection is actually more challenging than the previous one. Because we zoom in too much on the little granular detail, and if the image resolution is not good, one single model cannot give us a confidence predictions. That's why here we use the in-sum learning. The idea is that we train several weaker, smaller, lighter classifier, and then we use the in-sum learning to take the majority vote to get the final output. So if 2 of the model get it right and then 1 get it wrong, doesn't matter. It will take the majority vote and then give us the correct output. And then the weak learner we include here is the XGBoost, the random forest, and support vector machines. So each of the model by itself, it's relatively lightweight and it's not that powerful. But when we combine them with the in-sum learning, they will give us the majority vote and give us the more accurate result. And after we train the model, we input any OMSN data set, and then we look at the curve nodes. We will sample around the curve node for the image patches, and then we'll classify as positive or negative for if there's a tactile paving around that curve nodes. So that's the evaluation we have on the unseen data set. About 80% of them are right. We also have the similar challenges as before, lower image resolution and shadow coverage. And we are using a similar approach to try addressing this. And our extension number 3 is sidewalk width estimation. So as Suresh has mentioned, we have just for the Washington state, we have produced hundreds of thousands kilometers of sidewalks. And then if we need to know the width of the sidewalk, if we have a human mapper to manually go over each one, do measuring and then entering, it's very time consuming and costly. So the idea here is to use AI or machine learning to automate this process. So we can just let the machine go through every single line string on the OSM and then assign the width to the sidewalks if it's not already exist. And here's just an overview of how this works. Again, we use aerial imagery as input, and then here we pass it through a semantic segmentation model, which gives us the pixel level predictions on where the sidewalks are. Now, and then we can combine this pixel level information with the geographic bounding box of this image, and then we sample around the sidewalk. We can get the estimated sidewalk width at each point. And then when we gather all these data points together, we can use the internal density estimation to give us an overall distribution of this sidewalk. And then here we are taking the peak of the distribution to represent the width of this sidewalk line string, and this is the number that we can enter back into OSM. And in addition to that, we also output the narrowest width in the cases there's a variation in the width within one single sidewalk line string. We are doing this because we found that it's very useful in some of the accessibility focused application. For example, a wheelchair user would like to know if some sidewalks has the minimum width required for them to traverse. And here's the evaluation. When we compare to the ground truth, we're able to get a very tight distribution with our error center around the 0, and then have a mean error of less than half a meter.
That's 3 pixels in the imagery.
Yeah. Yeah, and then with this, I'll hand back to Suresh.
Yeah, as Ricky mentioned, we do have some improvements to make, and one of which is we want to expand the type of markings that we are trying to classify. That again, that's one. Number 2 is obviously like anywhere we have occlusions or shadows and such, we cannot detect properly, so we are trying to fuse from street imagery to get those details. And we do have very rich data that is tagged, and I don't think the OSM has that, right? So we are happy to work with the local communities to get this data into OSM, so if anyone is interested, please come and talk to us. And if you want to see the data, that QR code will take you to the statewide data set, so please feel free to explore. And thank you. On time?
Yeah.
1 minute left. If anyone has a quick question, we have 1 minute.
I think the question is, yeah. I think the question is, will we be interested in working? Oh, the data is public. I mean, you need a sign up, but it can be taken by anybody. And we would work. We already have OSM chain set creator, so we can actually give you OSM chain set, and you can upload it. But as OSM community requires, it has to be manually verified. So, yes. So any local communities, please reach out to us. Jake?
Can you speak into the mic so we can hear you right there? And can the next speaker please come up? What?
You can tell us when to stop.
Okay. Last question.
So, sorry, I'll be quick. So, for example, the estimations of sidewalk width that you were showing are really cool to see, and that's the type of difficult calculation to make, even when manually mapping, even if I'm right there at the sidewalk, right? So I'm wondering if that's the type of tool you all would be willing to or able to share with the community in the future. Is that something you've considered?
We can talk about it for sure.
Yeah.
Okay. All right. Thank you, folks.